Today's topic is about factor analysis, the concept of factor analysis. But as you see here, we have two main type of factor analysis: exploratory factor analysis and confirmatory factor analysis. Exploratory factor analysis is something that we perform in SPSS, and we call it factor analysis. But actually, this type of factor analysis is exploratory factor analysis. We have another type, is confirmatory, and we develop item based on theory and the literature, and we apply some criteria for assessment of reliability and validity. So that method is called the confirmatory factor analysis. Here you can see the difference between confirmatory factor analysis and exploratory factor analysis. For example, if you have a pool of items, a pool of questions, right? Here, for example, you have 8 items, and you don't have any literature to support association or connection between each item and the construct. You don't know among x1 to x8 which items belong to y and which items belong to z. So you don't have any literature to support it, right? If you don't have literature to support connection, association, and link between items and construct or variable, latent variable, and you want to explore which item belong to which construct, we need to run exploratory factor analysis. So exploratory factor analysis is for some cases, for some situations that we don't have theory to support connection of items and construct, right? But confirmatory, similar to a figure in right side. Okay, here you can see we have one x1 to x8. We have a pool of items without knowing which item belong to y or z. So here is this can be an example of exploratory factor analysis. So when we apply exploratory factor analysis, we actually try to categorize items under some construct or latent variable. But if we have literature, if we have some support that, and we know based on prior knowledge, we know x1 to x4 actually belong to y, and x1 to x4 represents the meaning of y construct, right? And x5 to x8 belong to z, so represents the meaning, establish the meaning of z latent variable. In this case, we have to run to check reliability and validity, or to check based on literature we know, but still in our context, based on our data set, we need to check that these items correctly, based on our data, can represent y, or these items can represent z. So for this case, we have to run CFA, confirmatory factor analysis. Confirmatory factor analysis, not EFA. So we have these two main types of the factor analysis. EFA is actually performed, as I mentioned, in SPSS, and when we don't have theory to support. But CFA actually is performed in concept of structural equation modeling. When we have a structural equation modeling, when we apply a structural equation modeling or SEM, CFA is one important step of SEM to check reliability and validity of items to measure or to represent each construct that we adopted from literature, we adopted from previous studies, right? So if you adopt item for your variable, you have loyalty, you have satisfaction, you have image, for example, destination image. So you adopted some item to measure each construct from previous studies. And you know item 1 to 3 measure satisfaction, 4 to 6 measure loyalty, and 7 to 11 measure image, right? So you don't need to run EFA. And performing EFA is not meaningful because actually you already know what items belong to what construct. So in this case, you have to run CFA, confirmatory factor analysis, to confirm belonging of these items, association of these items to each construct, to loyalty, to satisfaction, and to image, right? So this is the main difference between CFA and EFA. But now, because we are working on SPSS and first generation of analysis technique, we want to see a performance. We want to see how we can perform EFA, exploratory factor analysis, right? So factor analysis that here we mention is exploratory or EFA. EFA or exploratory factor analysis actually, as I mentioned, is a type of statistical method that we apply to categorize or to check items, a pool of items under some categories that we call these categories factor. So if we have 10 items and we run factor analysis to see what items measure which component, 3 items measure component 1, 4 items measure component 2, and 3 items measure component 3. And we call these 3 component factor, right? So because of that, we call this method factor analysis to identify factors that items belong to these factors, right? So we apply actually factor analysis for abstraction to reduce number of variables because we categorize items, 10 items, for example, under 3 factors, 3 categories, 3 new variables, right? So we abstract our framework, our model, and reduce number of relationship, number of hypotheses, and the complexity of our model. And also we can understand what items can measure which construct, which factor, or which component, right? So this is the main reason that we apply factor analysis. But factor analysis is only for reflective construct. You remember we discussed, I think, in second or third session about reflective and formative construct, right? Measurement in quantitative research. And we discussed latent variables can be measured in different ways. The example that I explained for you was satisfaction. And we actually discussed satisfaction can be measured based on two types of items. Satisfaction can be measured based on some items that are highly correlated. For example, I'm satisfied with this hotel. I will recommend to my friend. I'm happy to stay here. So these items are highly correlated. And also satisfaction can be measured by another set of items that are not necessarily correlated. We can measure satisfaction based on satisfaction about different aspects of hotels, about environment, satisfaction with personnel, satisfaction with room equipment, satisfaction with accessibility, satisfaction with service. So when we measure satisfaction based on different aspects, these aspects and satisfaction of these aspects actually are not necessarily correlated. I can be satisfied with service, but not with personnel. I can be satisfied with environment, but not accessibility of hotel, right? So are not necessarily correlated. This type of measurement model or this type of items to measure a variable is formative items and formative construct. We discussed that for reflective, we consider and the important parameter for assessment of reflective construct is loading. Loading. Later we will go through this one and see what this loading means. But for formative construct, loading is not important. For formative construct, you remember, construct x1, x2, and x3 form a construct together. So the direction of arrow is from item to construct. So for formative construct, weight is important, not loading. Weight is important. But for reflective, loading is most important parameter. Okay, so when you say, when we discuss, when we want to perform factor analysis, we assume that our variable, our construct or latent variable are reflective, not formative. Because factor analysis work based on loading, not based on weight. So we apply and we assess loading for factor analysis. So factor analysis, when we apply factor analysis, we assume our construct is reflective. And this is mathematical equation or representation of relationship between item and reflective construct in factor analysis. In factor analysis, we have this lambda. So this is loading. X1 is item. We have error term and we have construct. And each item is actually For each item, we have a regression equation. Again, here we go back to regression. So regression is not only for regression analysis. In many of the statistical techniques, we actually need to know the meaning of regression, and we apply premise of regression analysis and regression equation. Okay, so here x1 is lambda 1 x, or let's say this one is x plus error. So here is regression equation for relationship between x and x1. Also x2, right? x2 and x. Here you can see x3 and x. So based on this lambda 1 is similar to what in regression equation?
Beta coefficient.
Hat coefficient is similar to beta coefficient or regression coefficient, right? So this is regression coefficient. And this regression coefficient show the relationship between x and x1. But when we have simple regression, actually this regression coefficient is also correlation coefficient. Correlation between x and x1. Correlation between x and x1. So this lambda 1 show correlation between item and correlation between constraint. And also this lambda to the power of 2 squared lambda. This squared lambda is variance that explained by x on x1. So based on this lambda, we can understand, we can measure how many percent of variance of x explained by x1, right? So x1 include how many percent of variance of constraint. So because of that, squared loading also is very important. Squared loading explain and show the common variance between x1 and x, between item and constraint. So later we'll see in the literature in first stage, we say lambda should be, this loading should be higher than 0.7 to be acceptable. Lower than 0.7 also is acceptable, but the best is higher than 0.7. Why? Because when we say lambda higher than 0.7 is acceptable, squared lambda, this 0.7 to the power of 2 will be 0.5, almost 0.49 something. So it's almost 0.5, means x1 and x2, x1 and x has 50% shared variance, 50% common variance, right? So this lambda, this loading is very important for factor analysis. And this loading shows shared variance, common variance of x construct and item. So based on this, we run factor analysis and we calculate this loading. And based on this loading, we can identify what item has highest share variance, common variance with factor. Okay. For example, here, okay, when we run factor analysis and we find x1 belong to y, means among these 8 x1, x2, x6 and x7 has these 4 items have highest common variance with y, and we understand, we identify this one based on loading. So loading is very important in factor analysis. And again, this is for reflective construct, because for formative, we don't assess loading, right? Okay, the concept of factor analysis is clear, right? Okay, but how we calculate this loading, there are different methods and different algorithms. You cannot calculate, and you don't need to calculate manually. You can choose some of the algorithm, and based on those algorithms, software can calculate loading for you. But you need to understand the interpretation and the meaning of this loading. So this explanation is to understand the meaning of loading and how actually we can interpret this loading in factor analysis, right? To create this factor and also to calculate this loading, there are different methods. This is 2 common methods for calculation of factor and then calculation of loading, because loading and factor are related. So principal component analysis, or PCA, or principal axis factoring, or PAF, are 2 main methods to calculate, to identify factor and to calculate, based on those factors, to calculate loading. You can choose these 2 methods, but the most common method is PCA. Also, you can change to PAF to calculate, to create factor and actually to perform factor analysis. There are 3 actually criteria for identify number of factors. So when we run factor analysis, we get some values and some parameters and some we have result for some criteria. Later I will show you there are 2 main factors for extracting factor or to identify number of factors. One is the value of eigenvalue actually, and eigenvalue should be higher than 1 for each extracted component. So if when we go to software, you can see actually software can create more than a specific number of factors, but only we choose the number of factors that eigenvalue of these factors are higher than 1. But what's the meaning of this one? Roughly, this eigenvalue means the variance of factor that we extract, we create based on items, at least should be higher than variance of one item. Should be at least higher than variance of one item. If it's lower than variance of one item, it means it's not meaningful to create this factor, because this factor, the variance of this new variable and new factor, is lower than even one item, variance of one item. So what's the reason, what's the meaning that we create this factor and we accept this factor? So the eigenvalue should be at least 1 and higher than 1. So when we run factor analysis, we select factors with eigenvalue of higher than 1. And we skip other component, other factors. Don't consider other factors. Another method is the Scree plot. I will show you how we can see a Scree plot. But generally, we use the eigenvalue for number of items more than 20. But number of items less than 20, we can use a Scree plot. But most of time, the result of Scree plot and eigenvalue is very close. Sometimes there is one factor difference where Scree plot identified 8 factor, for example, eigenvalue identified 7 factor, right? And the third one actually is based on theory, but if based on theory, we can categorize items, and based on theory, we know what items belong to what construct, what component. So actually, this should not be factor analysis, exploratory factor analysis. If we know this one, we have to go for confirmatory factor analysis, right? So the third criteria is not very meaningful, at least based on my knowledge, because based on my understanding, when we have theory to support the connection relationship between item and construct, so doesn't need to go for EFA, and we can go for CFA, right? So these two are two main criteria. Okay, this is the table from software. Later I'll show you. This is a Scree plot. Software give this Scree plot to us based on a Scree. Okay, here we have the result of eigenvalue here. The first column is eigenvalue. Okay, this result has been repeated here. Okay, this eigenvalue, you can see for first factor is 6.5, second factor is 4.1, third one 1.7, 1.3, right? So for 4 components, 4 factors are higher than 1, but for fifth factor, factor number 5 is 0.97, 0.88, 0.79. So software extract more factors, but only the factors are acceptable that eigenvalue is higher than 1. So here you can see we have only 4 factors, right? Only 4 factors. And in this column, next column, you can see the variance of each, factor. Based on the number of items that assigned to a specific variable, a specific factor, and shared variance of items and factor, here you can see the percentage of variance of factor number 1. This 29%, 7 point means 29.7 means 29% of variance of all items. 29.7% of variance of all items are explained or represented by factor number 1. So factor number 1 is the most important factor, represent highest variance of items that we have. Second one is 19.02, means 19% of variance of all items are explained by factor number 2, factor number 3, 7.8%, and factor number 3, 6.1%. Here you can see cumulative result. So is 29.7. Second one is plus 19.025. Third one plus 7.8 and the plus 6.1. Right? So here you can see variance, explained variance by each factor. Later I will show you in software how we can get. So this is eigenvalue to understand number of factors. And this is the Scree plot. And this Scree plot, actually there are two ways to identify items. One is we identify here, this axis is eigenvalue. And this is the number of factors. Okay. The one method is, okay, we identify where is 1. Right? And see, for example, okay, when 1 cut this plot, and what's the number higher than 1? Okay, so we can see here is 4. Right? But another method, don't look at eigenvalue based on the Scree plot and see for what number the difference between two segments is not significant. So two segments are very close. Slope of two segments are very close. Okay. For example, here you can see after this point, we cannot see significant changes, right? So we cannot see significant changes for different items. So actually this refers to close eigenvalue for each item, for this point, number of items, number of the component, number of factors. So this is two-way. Okay, if we accept eigenvalue 1, so based on a Scree plot also will be 4. But if we see, if we check based on difference between segment, so this one should be number of factors. So the number of factors is 5. These two are from same data set. If we go back to this one, also we can see here factor number 5 is 0.972 and very close to 1. Right? So the result of eigenvalue and the result of Scree plot is consistent. Right? So, but we choose this one because eigenvalue can be more robust and better explain the connection between items and the factor. So the suitable number of factors for based on this data set is 4. Okay. So this is for criteria for number of factors. But actually, this is based on when we perform PCA, when we apply PCA or another method to extract factors, we can come out with the number of factors, and some items belong to each factor, but and loading for each item. But for factor analysis, to get more accurate result, actually we apply, after we identify main method for factor extraction, we apply some other method to rotate items and to get more accurate result. For example, if based on without rotation, we get some loading, but after rotation, loading will be changed and we can get more robust and more accurate result. There are two types of factor rotation: orthogonal factor rotation and oblique factor rotation. And under each one, we have a few types: Varimax, Equimax, Quartimax. And under oblique, we have direct oblique and Promax. So what's the meaning? Actually, these different methods apply different algorithm for rotation of items and to calculate loading. This is a type of rotation for items based on first stage when we identify item and when we identify loading. So we apply this type of rotation. But when we have to use orthogonal rotation and when we use oblique rotation, is based on the correlation of extracted factors. If factors that we extract, if factors that we identify are correlated, and correlation between factors at least is 0.2 and higher, we have to use oblique rotation. But if factors are not correlated, we have to use orthogonal rotation. So we can, after factor extraction, we can see correlation between factors. And if factors are correlated, so we have to apply oblique rotation. And if already we apply oblique rotation, so it's fine. But if we identify it's not the factors are not correlated, so we have to choose another factor rotation method. Okay. Okay, later I will go back to here, number of items, and okay, let's finish this part and then go to solve. Sample size for factor analysis. How many samples we need to run factor analysis? So there is a minimum sample size. Different literature actually recommended different rule of thumb and different threshold. But one of the common threshold is 5 to 10 times of number of items. For example, if you have 20 items, and you want to run factor analysis for these 20 items, you have to at least have 5 times of this 20, 100 to 200. So 100 to 200 can be minimum sample size for performing analysis, performing factor analysis. Another rule of thumb from literature is if communality. Communality is correlation between items and extracted factor. For example, item number 1 belongs to factor number 1. So correlation between items and factor without rotation and before rotation is called communality. So if communality of all items are higher than 0.6, so means items has good connection, good link with factors. So literature says 60 cases should be enough, but don't trust to these values. If communality is lower than 0.5, so we should go for 100 or 200 cases. But the first one can be more accurate compared to others. So it depends on number of cases, number of items that you have. So this is for minimum sample size to run factor analysis. This is communality table that we can get from our analysis. This is another criteria that we need to check for factor analysis. First criteria is this Kaiser-Meyer-Olkin statistic or KMO statistic. KMO statistic is for testing adequacy of your data. Okay, here we discuss minimum sample size, right? But when you have a sample, but you are not sure this sample is enough for performing analysis, you can use this statistic. You can use this criterion, KMO. And if this criterion is 0.9 and higher is excellent. So means your data is very good to run factor analysis. Number of your samples adequate to sufficient to run some factor analysis. 0.8 is good, 0.7 is average, but 0.6 and less than 0.5 is weak and actually not acceptable. So to run factor analysis, we have to get the value of KMO higher than 0.8 to be in safe side. So we can say our data is sufficient to run factor analysis. Another criterion, another test is Bartlett test. For this Bartlett test, actually we check significance of this test. This Bartlett test of sparsity, if it's significant, means p-value here is lower than 0.05. If lower than 0.05 and significant, means our items are suitable and actually related to each other and suitable to perform factor analysis. So our items are related to each other enough to run EFA, to run factor analysis. So this KMO for adequacy of data, and this Bartlett test for significance of this test to check the suitability of our data, appropriateness of our items to run factor analysis. So if it's significant, means we can run factor analysis for these items. So these are two criteria for, actually we need to check and report before reporting result of factor analysis. All right. Okay. And this is KMO and Bartlett test. Last part for factor analysis, how many items actually should be if we go to variable view. Actually, in the data set that we use here is we adopted from previous studies. So in a real study, we don't need to run factor analysis for this type of item. And we can run confirmatory factor analysis, not exploratory factor analysis, right? But only for practice and for assignment, we assume that we have these items from 8, CA1 to 14. So we have 33 items, right? But we don't know, we assume we don't know, and we have no prior knowledge to categorize these items. So we want to run factor analysis and see what items belong to what constraint. Actually now, based on our knowledge and based on this information that we know we've adopted this item from previous studies, we can check and we can cross-validate result of factor analysis and our knowledge and information. And see, when we run factor analysis, factors, items under community attachment will categorize under one component and environmental attitude another component, or we get mix of items. So we can cross-validate result of factor analysis based on our information in this case, right? But we assume we don't know, we have no prior knowledge, and only we want to run EFA to categorize these items under, these 33 items under some factors, right? Okay. So for factor analysis, again, we need to go to analyze. Okay, one thing, for factor analysis, you have to work with items, not variable or construct that you created. Before you created this construct, community attachment, for example, environmental attitude for another test, right? So for factor analysis, you cannot use those variables. You have to use these items. We want to categorize these items, right? Okay, we need to go to
Professor here, and may I ask a question?
Yes.
Yeah, since you know, as in assignment 1, we have replaced some missing values and also deleted some outliers. And here,
Yes.
should we use
For all analysis, after dealing with missing value and replacing outlier, if you did, you use new items that you dealt with missing value, deleted outlier, and anything you have done. So you use those new items for your analysis.
Okay, thank you.
Okay, so for factor analysis, we go to dimension reduction. Okay. Analyze, dimension reduction, factor. So when we click on factor, this factor analysis box will be appear. So we transfer all items that we want to categorize, we want to do factor analysis to this variables box. So we transfer all to this. Right. Here we have some option. Descriptive. When you click on descriptive, only in descriptive part you have to tick KMO and Bartlett test. KMO and Bartlett test. Continue. Extraction. Extraction, in this method, you can choose different method. Two main method is principal component analysis, PCA, and the principal axis factoring analysis, PFA. But we keep the default. Default is principal component analysis. And here we tick on Scree plot. Okay. So we choose to we choose method and tick Scree plot. And rotation. When you click on rotation, you have several options here. Varimax, Quartimax, and Equamax are under orthogonal rotation. Direct oblique and Promax are under oblique rotation. Always, first you can choose oblique rotation, because based on result of oblique rotation, you can get correlation between factors. So, and among these two, Promax is the common method of rotation for oblique rotation. So click on Promax, keep kappa full, and just continue. Here you have options for later. We will go back to this part, but now just keep as default, and missing value we don't have issue. Continue and click on OK. Okay. So here we can see result of factor analysis. First table is KMO and Bartlett test. You can copy and paste in.
Sorry, you cannot see.
Oh, cannot
see the result table. Yeah, output is not there.
I have to share the screen. Now, can see.
Yes.
Okay, so the first table is KMO and Bartlett test. So you can copy and paste this table in for your assignment and for analysis if you want to use this table. Okay, so here result of KMO is 0.892. So it's very close to 9. So it's very good. So our data is sufficient to run factor analysis. So this is the first one. You have to explain and interpret also for your assignment. And result of Bartlett test, p-value is 0.000. So it's lower than 0.05 and significant. So our items are enough related to perform factor analysis. So our data and set of items are suitable to run factor analysis. So this is two criteria that we need to interpret at the beginning of factor analysis before going to the result of factor analysis for factors. This is a communality table. Okay, when you look at the communalities, you can see the communalities of all items are higher than 0.5. Okay. The lowest one is 0.62, I think. This one and this one. So we don't have issue with the communality. If, for example, one of the items, the communality is lower than 0.5, no need to do anything here, but probably this item will, if you have this problem, this item doesn't belong to any of factors. And later we will exclude from the factor analysis and the factors, extracted factors. So we can see this item with low communality doesn't belong to any of factors. Okay, but if we have all items, the communality of all items higher than 0.5, so it means should be fine, and we can categorize all items under some factor. Okay, so this is one of the main table for interpretation of the result of factor analysis. Okay, here first column, and also here you can see eigenvalue. So eigenvalue for 7 factors are higher than 1. So the number of acceptable factors for factor analysis is 7 factors or 7 components. Factor 8 is 0.87, so it's lower than 1. And others also low, so it's not acceptable to include factor number 8. And the variance explained by each factor, first one is the highest one is 32.13. Second one is 9%, 9.8, 8.6, 6.68, 5.2, 4.3, and 3.5% of the variance of all items explained by these components, first component, second, and total for these 7 components, 7 factors, 70.4% of variance of all items explained by these 7 factors, right? So this is the second, after eigenvalue, you can interpret this percentage of variance of each component, right? Okay, so this is a table for eigenvalue and explained variance by each factor. Now we can see this is a Scree plot. Before going to matrix for loading, this is a Scree plot. Okay, for a Scree plot, you can see one is here, but if we want to interpret based on a Scree plot, we should say 8, because after 8 we can see very, very low difference between segments. But before 8, actually we can see some difference between this segment and this one. But others, it's not significant. So based on the Scree plot, we should say 8. But actually, if we interpret a Scree plot with eigenvalue, also 7 should be correct number of factors. But here we have number of items more than 20. And when we have item more than 20, eigenvalue is preferred criterion for number of factors, right? So if you have more than 20 items, you can only interpret and explain eigenvalue and no need to report Scree plot. For your case, for your assignment, you have more than 20, right? So no need to report a Scree plot. But if you have less than 20, you can see what the Scree plot says and what's the difference between number of factor by Scree plot and by eigenvalue. Okay. Next step is loading. Now we want to see what items belong to what factor and what's the loading of items under each factor. Here we have 1, 2, 3 different tables when we apply Promax, when we apply oblique rotation. Okay, but before interpretation of these tables, we need to go to this component correlation matrix. This component correlation matrix shows correlation between factor 1 to 7, factor 1 to 7. So this is correlation between factor 1 and 2. This is correlation between factor 1 and 3, 1 and 4, 1 and 5, 6, 7. This is correlation between factor 2 and 5. So you can see many of correlation are higher than 0.2. Actually, all of correlation are on except this one. So most of correlation are higher than 0.2 and some of them higher than 0.5. So we have correlation between factors. So oblique rotation or Promax rotation was correct choice. Was correct choice. But if this table correlation is lower than 0.2, all correlation, so it means there is no correlation between factors. So if there is not correlation between factors, we have to go back to analysis and choose one of the rotation method under orthogonal. Varimax is one of the common. So we have to choose Varimax. But here we can see most of correlation are higher than 0.2. So Promax or oblique rotation is correct choice, is right choice. Oblique rotation, Promax rotation is the right choice. So now we can go to interpret this table. These three tables, actually, we can see loading based on different method. This one is before rotation. Pattern matrix is a combination of rotation and before rotation. But the best, structure matrix is combination of rotation, and before rotation, as actually it's combination of correlation and rotation. But when we apply Promax, pattern matrix is suitable table and most appropriate table to interpret. So the result of this pattern matrix is after correlation. So you can see loading after correlation. So this pattern matrix should be interpreted and explained, right? Okay. So if we go to this pattern matrix, for component 1, what we can see? Component 1, this is loading. This is correlation actually, or loading of this item on this component. So the loading of CA1 in component 1 is 0.03. So it's not acceptable. So we have to go down to see where we can find items for component 1. Okay. First item for component 1 is support 1. That is higher than 0.5. So in first place, we consider items with loading higher than 0.5 acceptable items for this factor. So here we can see support 1, 2, 3, 4, 5, 6, 7. All these items have loading higher than 0.5. Right? So support 1 to support 7 are items of component 1, factor 1. Under factor 1, we don't have any other component. We don't have any other item. This value called loading value under each factor, the item that belongs to factor 1, this is called factor loading. Loading of items on other factors. For example, this one 0.58 is loading of support 1 on factor 1. This is factor loading. But support 1 has some loading and shared variance and common variance with other factors. But this loading is very low. So this 0.123 is loading of support 1 on factor 2. We called this loading cross loading. Cross loading. So loading of each item on its factor, on own factor, called factor loading, like this one. But loading of each item on other factors, like this one, called cross loading. In other words, loading of each item on right factor, the factor that this item belong to this factor, loading called factor load. But loading on other factors that this item doesn't belong to those factors called cross load. Always loading or factor loading is much higher than cross loading. Always factor loading of each item is higher than cross loading on other factors. For example, for factor 2, okay, this is loading, but 0.024 is loading on factor 2, 0.039 factor 3, 0.035 factor 4, right? So here you can see loading and cross load. This is for factor 1. For factor 2, okay, let's go for factor 2. Factor 2, okay, here. For factor 2, we have loading higher than 0.5, actually 0.7 for PP1, PP2, 3, 4, and 5, right? Higher than 0.5. Sorry. Okay, here. Right? So we can see 4 factors, 4 items belong to positive perception. 5, 1, 2, 3, 4, 5, 5 items. And you can see loading higher than 0.5 and 0.7 for most of them. And the cross loading, you can see cross loading. Cross loading are much lower compared to loading. Right? So factor loading is loading on its own factor, and cross loading is loading on other factors. And always factor loading should be higher than 0.5, and always factor loading is much higher than cross loading. Right? Okay, but actually this table is a bit messy and crowded, right? We want to get a cleaner table and a very nice table to understand what item belong to what factor. And we don't need the cross loading. We don't want to see cross loading, right? If we want to get this type of table, okay, let's go back to analysis, dimension reduction, factor. We have all this here, but in option, we can sort by size. We can sort by size of loading, and we can delete cross loading or loading below this value. We can change this value. Here we can change this value to 0.44 because the value lower than 0.4 is not actually acceptable for factor loading, and we don't want to see cross loading. We want a clean table. So if we choose this one, all loading in the table lower than 0.4 will be removed from table. and only we can see loading higher than 0.4. You can put any value here, but 0.4 can be common value because lower than 0.4 is not acceptable for loading, for factor loading. So if we continue and okay, if we go to pattern matrix now, oh, we can see a very clear table, right? So we can see factor 1 is support, but loading of support 5, item number 5, is highest loading. It means item number 5 is the best item to represent support. If we assume this is if we get this is loading, right? So shared variance, common variance of this item with support will be 0.94 to the power of 2, right? So if we calculate this one, will be something 0.8, not sure, 34. So you can calculate 0.94 to the power of 2. So what's the result? Equal what? Okay, let me calculate 0.94. Okay, 8, right? 8, 3. So it means there is common variance between support 5, item number 5, and our variable support. 88% common variance. 88% common variance between support. So support 5 is the best item to represent support, followed by support 6, support 3, 4, 7, 2, 1. And support 1 only has about 33% common variance with support, but still acceptable. We can keep this item as long as the loading is higher than 0.5. We can keep this item. So here you can see these support items are categorized under component 1. Positive perception PP items categorized under 2, right? Third one, community attachment categorized under factor 3. Negative perception categorized under 4. Involvement categorized under 5, right? Involvement 1, 2, 3, 4. Economic gain categorized under factor 6. And environmental attitude categorized under factor number 7. So we can see all items that we already know that these items belong to each component. So now first component, what's the first factor? Now we know first factor is support. Second one is positive perception. Third one is community attachment. Fourth one is negative perception. Fifth one is involvement, economic gain. Sixth one, and number 7 is environmental attitude. Here we can cross-validate all results because we assume we don't know. But actually, if we have prior knowledge, we can see, okay, this is correct. These items correctly categorized under these main component and variable, right?
Prof, can I ask a question?
Yes.
As we can see from the table, CA1 is lower than 0.5. So how can we analyze this?
CA1.
Yeah.
It's up to you. If it's lower than 0.5 for formative construct, for reflective construct, you can delete this item. You can decide to delete, because contribution of this item actually, or common variance with community attachment, is very low. But some of the literature also suggests that still you can keep higher than 0.4 if other items have high loading. If it's higher than 0.4 and other items have high loading, you can keep this item. Another way to check if it's higher than 0.4 and reliability of this component based on this item is higher than threshold, higher than 0.7. Later I will show you how we can check reliability. So we can keep this item.
Okay.
But lower than 0.4, there is no room to keep item lower than 0.4, and we have to delete. We have to delete for further analysis, for future analysis. If we want to run multiple regression, and first we run actually factor analysis, if an item has loading lower than 0.4, we have to delete this item and compute value or score of the variable based on remaining items. For example, here, if we delete CA1, we have to calculate community attachment based on 5 items, not 6. Okay?
Professor, you mean multiple regression should be based on the result of this factor analysis?
If you have any problem here and you delete any item in factor analysis, yes, later you have to compute your variable after deleting problematic items. If you have any problematic item. If you don't have any problematic item, okay, you can go ahead. No need to change anything.
Yeah, just like this one for CA1. And in the later regression, we should delete it, yes?
If CA1 is, if you decide to delete this one, yes. If you decide to delete this one, you have to delete and calculate the compute CA community attachment based on CA2, 3, 4, 5, and 6, and exclude CA1.
Can I just keep it here or remain here? That's okay.
If it's higher than 0.4, yes, you can keep it. But if it's lower than 0.4, you cannot keep it.
Okay. Thank you. That's it.
Professor, and this factor analysis are performed on data that we have already sorted out. We have already solved the issue of missing values and outliers and all those things, correct?
Yes.
Okay, thanks.
Okay, any other question?
Well, for the two tables, the original tables, which includes all of the items, and then this only the table which is much more clear. Just now this one.
Yeah.
No.
This one is before rotation. Here you can see then items. Here we have a messy loading and items. Most of items belong to factor 1, right?
Yeah, I mean that in the assignment too, and we have to copy both of the tables.
No, only pattern table.
This one.
Only pattern matrix, right?
Yeah. Okay, thank you.
Okay. If your components are not correlated, you have to go to your analysis and in the rotation part, change Promax to Varimax. If your component, your factor are not correlated. So continue and okay. Same table, KMO and Bartlett test is same, communality same, is total variance same, and you have two table here. Component is before rotation, and you have rotated component matrix. So you have to report this one. Rotated component matrix. Here you don't have correlation, and this table is something for calculation, actually, for the process of rotation, and so no need to interpret this table. Based on orthogonal approach or Varimax, we cannot get correlation between component. So to get correlation between component, you have to choose first the uplift or Promax rotation. Based on the value of correlation, if correlation is low, you can come to this option, and then you need to interpret this table. Here you can see the loading are slightly different with the Promax rotation. Okay? Because for Promax rotation, for example, SUP5 was 0.94, right? But here is 0.81. Or SUP6 was 0.91, but here is 0.81. So the algorithm is different, and so the value of loading will be different. Okay. When you perform factor analysis and identify what items belong to what factor, you have to check reliability of items under each component, under each factor, and report it. To check the reliability, again, go to analyze. And scale. So analyze, scale, reliability analysis. Right? So for reliability analysis, when you click, okay. So CA1 until CA6 was under first one factor, right? So you transfer this one. Don't get reliability of all items is meaningless. Reliability only you have to get for items under each factor. So we don't have overall reliability. I saw a lot in student, postgraduate student dissertation that, okay, they run reliability for each factor and also try to run reliability for all items. So it's meaningless, right? So for factor, one factor is community attachment, and you have these 6 items. Statistic here, we have different types of reliability, but in this table, in this box, actually you can use descriptive for item, and also scale. Scale means reliability, Kernbach alpha. If one item deleted, sometimes it's very useful because your reliability is low and you want to see if one item is deleted, what happened, how reliability changed. So you can choose this one. And here you have different type of reliability, but Kernbach alpha is the most common and famous reliability that we use, Kernbach's alpha. So Here, keep default and click on OK. Okay, so here you can see reliability for 6 items is 0.82. Cronbach's alpha and reliability higher than 0.7 is acceptable. So this one, this value should be higher than 0.7. So this one is 0.82 acceptable. And if you go here and see if you delete some items, if you delete item number 1, so the reliability will decrease. But for item number 6, the loading of item number 6 was lower than 0.5, right? So if you delete this item, reliability slightly will increase. So here is 0.82, will be 0.83. But this increase is not important and is not significant increase because already the reliability is higher than 0.7 and acceptable. So based on this also you can decide to delete one item or to retain it. Here, when you see the reliability is higher than 0.7 and item CA6 is higher than 0.4, so you can decide to keep this item. But if, for example, here the reliability is lower than 0.7, you can see 0.68, for example, and CA6 is 0.4 something, 43. And you see, if you delete this CA6, this reliability, this alpha will increase to 0.7. So in this case, you can delete this item to increase reliability to higher than threshold. Okay. So you can calculate reliability for each factor, not for overall again. So for second one, you can come to a scale again, reset, and the second one, for example, you want to see for positive perception. So when we transfer here, click on OK. So you can see the reliability for positive perception. Also, this one is higher than 0.7. But we didn't tick item deleted, so we don't have another table. Right? If you want to see by deleting one item what happened, here we have to choose this one. So we can see this item. By deleting some item, what happened to Cronbach's alpha? So this is for reliability after factor analysis. So when you identify items under each factor, so you can calculate reliability of items. Actually, factor analysis is to test validity. And when we apply Cronbach's alpha, we check reliability. So by both factor analysis and Cronbach's alpha, we can check reliability and validity of our items under each factor or under each constraint.